Hi Falcons, what we're going to talk about now is ionic and metallic compounds. Ionic compounds are held together by what's referred to as ionic bonding, which is created by the give and take of electrons. The ions are then held together by an attraction of opposite charges. For example, I have a sodium atom here with one valence electron that's going to form an ionic bond with a chloride ion here with 7 valence electrons. The sodium is going to give its one valence electron to the chloride ion. The sodium would then have a +1 charge. The chloride would then have a -1 charge, and they'd be held together by the attraction of those opposite charges. The result of this is not an individual molecule made up of 2 atoms. Rather, it's going to be an alternating pattern of positive and negative ions, where every positive ion is surrounded by negative ions, and every negative ion is surrounded by positives. You can see that three-dimensionally here as well, where this sodium in the center has 6 different chloride ions around it, and that's referred to as a crystal lattice. Let's talk for a second again about how these ions come together using Lewis dot structures. In the previous video, I showed you that magnesium in group 2A would form a dot structure with 2 valence electrons. Chlorine in group 7A would form an atom with 7 valence electrons. If they were to come together to form an ionic bond, what would happen is magnesium would give one of its valence electrons to this chloride ion. The chloride ion would then have a -1 charge and become stable, having a full 8 electrons in its outermost energy level. But the magnesium would not yet be stable. It would need to find another chlorine atom to give its other valence electron to, creating an additional chloride ion, again with a -1 charge. This magnesium that's given away 2 valence electrons would now have a +2 charge. The formula for this compound would then be MgCl2, but again, it would not form an individual unit. Rather, it would be a crystal lattice structure with a ratio of 1 magnesium for every 2 chloride ions in the entire crystal. Let's talk for a few minutes then about the properties of ionic compounds. Here's some images of various crystal salts. Salt is another term for an ionic compound. We typically think of salt, we think of this, which is table salt, but a salt is the generic term we can use for any ionic compound. Ionic compounds typically form very hard but brittle structures. They will shatter, but they will not bend. They are typified by cleavage planes, meaning when you put them under stress, they will break along one of these lines of these alternating patterns of positive and negative ions, and they'll shear along that line. Because every ion is held rigidly in place by this attraction to all of these nearby oppositely charged ions, they tend to have very high melting and boiling points. They will also conduct electricity, but only when melted or dissolved in an aqueous solution, when these positive and negatively charged ions are free to move around and move an electric charge through that medium. The next type of compound I'd like to talk to you about is what's called a metallic compound. Metallic compounds are described by what's called a sea of electrons. In metallic compounds, the valence electrons, so in this image, what you'd be thinking of here is, say, for example, a group of sodium atoms. Each of these positives would be representing a sodium atom and all of its inner shell electrons. Sodium, which is in group 1, would have 1 valence electron that's free to move around. Because the sodium atoms wouldn't hold those valence electrons very tightly, they would actually be able to move through this entire field. Because they're allowed to move through this entire field, it allows these ions to slide past one another, making metals able to bend and change their shape. It would also allow these metals to be able to conduct electricity, and I'm going to show you an image of that in this next slide. A metallic bond would be the force of attraction of this positive metal ion, or cation, to the surrounding sea of delocalized or free-to-move valence electrons. Some properties of metals would be that they are excellent conductors of heat and electric current. They're ductile, which means they can be stretched out in wires, and malleable, which means they can be bent. They can range from very soft to very hard depending on their ionization energy or attraction to that electron C. They can range in melting points from medium to high. There'll be solids at room temperature, with the exception of mercury. And they typically have very high melting points. In this image here, what I would like to show you is that ability to be malleable as a comparison to an ionic crystal. When hit with a hammer, a metallic compound, these metal ions with the sea of delocalized electrons around them can slide past one another, and the metal can be deformed or change shape, bent. The term we use for that is malleable. A crystal lattice with each of its ions held rigidly in place by those surrounding oppositely charged ions, if hit with that same hammer, would shatter. Thanks, Falcons. I hope this was helpful.